Hey everyone. I know getting started with Tidymodels can be frustrating, so I wanted to just record a video on basic modeling with Tidymodels for you to follow along with and hopefully gain some confidence here. So what I have is I've got a notebook that I've kind of scaffolded out, and we'll go through just the modeling process as you might experience it as you start modeling with Tidymodels. So I'm going to start by getting set up. I'm going to do the usual loading some convenient collections of packages. So I'm going to load the Tidyverse and I'm going to load Tidymodels. Tidymodels is our modeling ecosystem that we're going to use here in our course on regression together. I'm also going to do something perhaps a little bit weird. I'm going to load the Palmer Penguins data set. It's actually already loaded as part of Tidymodels, but I'm just going to load it so that it shows up here in my global environment. It's loaded when we run library Tidymodels, but it doesn't show up in the global environment. So all I've done here is make sure that we can see that data set. And the advantages to being able to see that data set are essentially that we can hit this blue circle with the triangle in it. We can drop down and we can see the columns that are available to us in the data set. And so I think that's all we need in order to get set up for our discussion today. We're going to take a look at data splitting. So here's your paradigm, your mental model for this. The idea is that we're constructing models that are going to go out and make predictions or to explain relationships, and we want those models to do a good job. The way we're going to do that is essentially by allowing the models to study from the data that we have available to us. But we also want to be able to assess how well that model is performing. So we want to take some of the study materials and hide them off to the side. This will allow us to test our model just like as if you were studying for an exam in a class that you're taking. You would study from the materials that are available to you. You would not know what the exam is going to look like, so you don't want to be able to study exactly the exam questions because you don't actually have access to them. And so we're going to take some of our data and move it off to the side as if it's part of a hidden exam. And actually, ideally, you would probably love to have access to a practice exam. So we're going to do that as well. So we're going to take our penguins data and we're going to split it into three pieces. So what I'm going to do to start is I'm going to set a seed. Setting a seed is a very useful thing to do whenever you're doing anything that's random. And we're about to randomly split our data into these three piles: a training set that we can learn from and study from, a test set that will serve as our practice test, and then a final validation set that will serve as the ultimate exam that we're going to have the model take. Again, that will give us some insight into how well the model is performing and whether the model we've constructed has learned appropriately, or if it has been too sensitive to the training data, it's overstudied the practice questions and just simply memorized those, which we want to avoid. So again, I'm going to start by splitting this data. I'm going to start by declaring a data splits object, and I'm going to use the initial split function that's part of Tidymodels in order to do that. There is a different version of this function that will split into three sets automatically, but we're going to use initial split moving forward because we're going to slowly decide that actually this three pile split is not actually what we want to do. We still want to have just two piles, but for now, three is what we'll use. I'm going to use initial split. I'm going to split the penguins data, and the proportion I'm going to use is 75% for training. There are some other parameters that initial split can take. We're not going to use any of them here today. So what I'm going to do is I'm going to split that then into training data. So I'm going to call the training function on data splits. And I'm going to collect the remaining data into this temporary set that we're going to split again. The function to collect the other data, the remaining 25% of observations, is called, that function is called testing. So we'll grab the testing data from there. Next thing I'm going to do is I'm going to split the temporary data set again. So data splits. I'm just going to overwrite that split object. Actually, let me do this. I'm going to do temp splits so that we can see everything that we've done. So I'm going to use the initial split function again. I'm not going to split penguins this time. I'm only going to split the temp data. And I'm going to use 50% this time. I'm just going to take 50% of my remaining observations and move them into the test set that will serve again as our practice exam for our model. And then the remaining 50% of those observations will go into the validation set, which is sort of like the real exam. And so now that we have those temp splits defined, we can go and grab the test data. This is a little bit weird because the terminology is not matching the function names, but I'm going to take the training piece here that came out of initial split. I'm going to take that portion of the temporary data and put it into test. And then the validation data is going to be the testing data on temp splits. Now, I didn't run any of that, so you didn't see any changes being made up here to the global environment. As a reminder, there's a few ways that you can run code. If you're on a Mac, you can hold down Command and hit Enter. That will run an individual line. If you're on Windows, you can hold down Control and hit Enter. That'll do the same thing. Or you can come up here and click that green play button, and it will run all of the code in the current cell. I'm just going to run line by line so that we can see what's happening. So set.seed sets the seed for the random number generator. This ensures that I will get the same training and testing and validation rows every time I run this script. And you will also get the same if you choose to run this on your computer. Now I'm going to mark the rows of the penguins data frame as belonging to training or temporary sets here. And then I'm going to collect the training rows and I'm going to collect the temporary rows. And so you can see that the original penguins data frame had 344 observations, and now it's been split into a training set that has the majority of those observations, 258, and the temporary set has 86. And if we add 258 and 86, we'll get the original 344. So we have just split this data. All right. The next thing I'm going to do is I'm going to split the temporary data set into two halves, and I'm going to do them into two equal halves. That's what the proportion being equal to 50% here is doing. I've got the temp splits, I've got the test set now collected, and the validation set collected. And so you can see a few things up here. We have the training data, 258 observations. We've got the test data, that's our practice exam. There's 43 penguins in that data set. And then the validation data, that's the ultimate test for our model. We won't access that, actually either of those data sets today in this video, but we may in a future video that has another 43 observations. Because I ran some code down here in the console, I'm just going to rerun all of this all at once to make sure that the seed flows through to all of these lines of code, and we really do get the same penguins in the training, test, and validation sets. All right, so again, that's splitting our data here. The purpose is to give us a set that we can study from. That's the training data. We can learn as much as we want through that. We'll do exploratory data analysis there. That's calculating summary statistics, drawing data visualizations, interpreting the relationships that we're finding. All of that happens on the training data, and also the model fitting happens on the training data. So the training data is where we do most of our work. The test data serves as a sort of intermediate battleground for our models. We probably are going to build multiple models here throughout this project. And so we'll take each of the models we build, we'll apply them to the test data, we'll see how they perform. This will allow us to do two things. First and foremost, it's going to allow us to make updates to our models to try to improve them over time. Second thing it's going to allow us to do is it's going to allow us to choose a best model or a best series of models that we decide we want to move forward with. Once we decide the model or the series of models that we want to move forward with, we can apply those models to one last test set. This is the actual ultimate test that we're giving our models. This will ensure that our models are performing as we expect them to. If the models perform much more poorly on this validation set than we had expected through the analyses we've run on training and test data, then we'll know that we have some work to do to go back and figure out why that is. Perhaps we've overfit, which we want to avoid. All right. So for the rest of this video and for the majority of our time together, we're going to stick with the training data. The training data will be, again, what we learn from. Exploratory data analysis, EDA, is usually what comes next. EDA should only be done on your training data. You're learning about your observations while you're doing the EDA, so this is part of the learning process, part of the training process. You are an extension of your model. So even though your model may not see all of the data, if you do the EDA using all of the data or looking at the other data sets, then you're going to leak that information into the model and you're at a higher risk of overfitting your model. Overfitting essentially is going to mean that your model, you have expectations that your model is going to perform much better on new data than it actually will, because your model had access to information about future observations that it really shouldn't have when you were training it. We're going to skip EDA today. It's not the purpose of this video. We're going to skip right to constructing models. And constructing models is all we'll focus on today. So we'll start with simple linear regression and we'll move to multiple linear regression. I'll show you how to construct both model types using Tidymodels. Nice thing for us is they're nearly identical to construct. So we'll start again with simple linear regression model. This is the most basic type of linear regression model. It includes one predictor, and that predictor is going to be numeric. We're going to try to predict some response using an intercept, beta 0, plus a slope coefficient times that predictor. This really is just a straight line, even though we're using some funny symbols here. So E stands for expected response. We're acknowledging here the fact that our data is noisy and we're not going to be able to fit a model that goes through all of our data points exactly. And in fact, we don't want to do that. So we're predicting the expected response or the average response here. Beta 0 is your intercept again. So that's like the b value in this y equals mx plus b straight line formula that you're familiar with from algebra. Beta 1 again is a slope. So beta 1 is your m value. That's here. And your predictor is like your independent variable. It's your x. So we are really just fitting a straight line model. We're using the Greek letters beta here because these are population parameters that we are going to use data to try to estimate. So the population has some intercept and it has some slope. We're going to estimate them using our training data. All right. So we'll build a model just like this one. What we're going to do is we're going to build a model that tries to predict penguin body mass. I'm going to update this model form so that we can see it. It's going to predict penguin body mass using flipper length. So don't pay attention to where I'm typing, pay attention to down below here. So we're predicting body mass and we're using flipper length. So the ultimate model we build will have a slope coefficient attached to flipper length that will tell us how changes in flipper length result in an expected change in the penguin body mass, and will also have an intercept. So now we're on to Tidymodels and trying to construct this model. Tidymodels modeling framework has just a few basic components. We're always going to start with a model specification. This is going to determine the class of model we build. For us in this video, it's going to be linear regression, but there are many, many other types of model that you can construct. Linear regression is not the only one, and we'll see more later on in our course. After we just declare the model form or the model class, we're going to identify a recipe. Our recipe is essentially a formula, and it's a formula that declares the output, the response, and the available inputs. Those are our explanatory variables here, or our predictors. And then eventually, not today, but eventually, we'll use the recipe to declare some feature engineering steps. Feature engineering just allows us to declare how we are going to use our explanatory variables or our predictors. We can change how they're being used in the model. But for today, none of that. We're just declaring the model output and the available inputs, along with where to find them. After we have a specification and a recipe, we'll package those things together into what we're calling a workflow and what Tidymodels calls a workflow. And the workflow is actually what's going to be fit to the training data. So we'll fit the workflow to the training data. It's important that you fit to the training data and you only ever fit to the training data. This is all we want to do. This is allowing our model to go out and study and learn. We don't want our model to learn from the practice test. We want it to try to execute on the practice test, and then we'll analyze how well it performs. And we definitely don't want our model to go out and learn the questions that are on the ultimate validation set. We want those to remain hidden throughout this entire process. So this is the Tidymodels modeling framework here that we're going to run through. The hashtags that you're seeing me use in front of each line here so far is the comment character in R. So R ignores everything after these comments. These are just notes for us. You don't need to include them in your code. So I'm going to start with a model specification. I'm going to use SLR here for simple linear regression and spec for specification. It's really common to sort of suffix your model specification with _spec. I see lots of people doing that. I see that happening in the documentation for Tidymodels too. So I'm going to try to be consistent here with what you'll see when you go out and look at extra resources. So our simple linear regression specification is going to be a linear regression model. And this next step that we're doing is not necessary for linear regression, but it is going to be necessary as we move forward. So I want to get us in the habit of doing it. I'm going to set the engine for this to LM, linear model. Setting the engine determines the math that is going to be done behind the scenes to identify the best possible values of these beta coefficients. Later on, we'll change what package or what strategy R is going to use behind the scenes in order to do the math differently to allow for different constraints on our model. So we've declared a linear regression model, and we've declared how the math is going to be done behind the scenes in order to discover those beta coefficients. For us here, the intercept and the slope attached to flipper length. I'm going to run that, and you'll see that we have this model specification here showing up on in our global environment. Now that the model specification has been declared, I'm going to declare a recipe. So again, I'm going to try to be consistent here with Tidymodels documentation. So _res is the way people will typically suffix their recipe to identify what container contains which type of object. So the SLR spec object contains a model specification. The SLR res object contains a recipe. And so we're going to declare that using the recipe keyword. Formula is going to go in here. So the first part of your formula is your output, the response that you're trying to predict. I'm going to check in with our training data to make sure that I get the variable name correctly. Whatever you pass to recipe has to be a valid column name in your data set. So I've got body mass G. That's my output. That's going to go to the left of this tilde. The tilde you get by using the shift key and the key next to the number 1 on your keyboard. In R, I typically think of that tilde character to mean as explained by. So I'm looking for body mass as explained by, and for this model, we'd like to use flipper length. And the column name there is flipper length mm. We've got to give one more thing to our recipe, and that's to tell the recipe function where it can look to find these columns. So the data that we're using can be found in train. And generally, this is what you're going to do. The data argument passed to your recipe function should be your training data. At this point, our recipe is finished. So this tells R, we're going to try to construct body mass or to predict body mass as explained by or using flipper length in millimeters as our only predictor variable. And having just one predictor variable here on the right-hand side of this formula is what indicates that we're going to be using simple linear regression in conjunction with that linear regression model class. So again, I'm going to run that. Now I have not just SLR spec, but I have SLR res. With the model specification and the recipe both constructed, we're going to package these together into a workflow. So I'm going to do SLR WF. You'll notice that all of these objects that I'm building start with SLR. This helps me identify that these objects go together. So they all belong to the same model that I'm building, and underscore WF here is indicating that I have a workflow. Again, whatever appears to the left of these arrows or equal signs if you prefer, R does not care about. R will allow you to, within reason, define whatever variable names you want. Some things are prohibited, like spaces and variable names. So you'll notice I'm using the underscore here. But whatever appears to the left is your choice. There's nothing special about SLR underscore WF other than my strategy of saying, okay, SLR is simple linear regression. Every object that I've created that corresponds to this simple linear regression model has a name that includes that at the start. And then underscore WF here is indicating that this is the workflow object. So as I'm creating this, I'm going to start with the workflow keyword. I'm going to pipe that into a function called add model. Inside of add model goes your model specification. So that's SLR spec. And then I'm going to pipe that to a function called add recipe. And inside of there goes your recipe. This is how constructing your model workflow is going to look every time. So you start with the workflow function to create a workflow, then you add the model to it, and you add the recipe to it. I'm going to run this command, and again, you see now that in my global environment, I have simple linear regression workflow. Once we have the workflow built, we can fit the model to our training data. This is a spot where you've got to be careful, so I'm going to use SLR fit. I am going to define this as my workflow. I'm going to pipe my workflow to the fit function, and I'm going to fit that model to our training data. Again, always inside of fit should go training data, should never be anything else there. So I've now fit my model to my training data, and I have this SLR fit object here. That is all it takes to build a a regression model here using the Tidymodels framework. So again, you always start out with a model specification that determines the type of model you're building. For us, for right now, that is going to be a linear regression model always. Later on in our course, I'll show you how to access other types of model class. Linear regression is not the only way to predict a numerical response. And I'd like you to get in the habit of setting the engine here. What that's doing is it's determining the math behind the scenes that's going to be used to fit your model. In terms of regression models, or linear regression models, I should say, that is the math that's going to be done in order to solve for these beta coefficients. After you have a specification, you'll create a recipe. That recipe at a minimum is going to contain the formula that you're using to make your predictions. That formula has in it the response that you're trying to construct or predict. So we're trying to predict body mass, and any of the variables that you're using to predict that response or to explain that response. And so here we're using flipper length. In between the response and your predictors goes the tilde. And we'll take a look at what it looks like in order to include more predictors shortly when we hit multiple linear regression. Additionally, inside your recipe function will go a declaration of where to find those columns. So those columns, again, body mass G and flipper length MM, must appear exactly as you've written them inside of your data set. All right. After you have the specification and the recipe, you package both of those things together into a workflow. This will never look different. We'll always use the workflow function, add the model to it, and add the recipe to it. A common mistake here is to use some copy and paste and then accidentally put the model specification again inside of the recipe function, or put a recipe inside the add model function. In those cases, you'll get an error indicating that, hey, inside that recipe function or add recipe function must be a recipe object. It can't be a model specification. So just check if you're getting errors. That is almost surely what's happening here. And then again, we'll finish this up by fitting our model to our training data. All right. So again, that's a lot that we've done. We have fit a model to our training data. That model is a simple linear regression model. Let's move forward and let's take a look at what that model looks like. I'm going to save a couple of things for potentially a different video. I'll record one if you guys like this one and want me to record additional ones. So the global model assessment and then the term-based model assessments, we'll save that. Again, I'm not going to do it here because this video will be long enough just on its own. So let's just examine our fitted model below. So what I want to do is, now R knows what my model looks like. I want to know what it looks like. So I'm going to take that SLR fit object and I'm going to pipe it to a function called extract fit engine. And I'm going to pipe that to a function called tidy. Tidy is going to give me more information than extract fit engine on its own would give me, and it gives it to me in a nice format. So now I get some information about the terms that are in my model. I have an intercept term, and I have a term corresponding to flipper length in millimeters. That's good, because when we set out to do this, I had an intercept term and a term corresponding to flipper length. I have the standard error for those. Before I go to standard error, I should talk about the estimate. I have the estimates. These are the estimated beta coefficients for my model. We'll fill those in shortly. I have the standard error for those estimates. So this is an estimate of how much uncertainty there is with the values for those estimates. I have a test statistic that goes along with a test, and a p-value that goes along with that test as well. These tests are attempting to determine whether or not that beta coefficient is 0. And so, again, we'll look at those tests formally, potentially in another video if you'd like me to record one. But for now, let's just take this estimate and build our model. So the estimated model now, again, look at the bottom of my screen here where you can see the nice text, not the uh, sort of code here that I'm typing. So I'm going to replace the beta 0 coefficient with what I now know my model has learned. My model has learned that intercept value should be around negative 58, 68, and let's say a half. And so there is my estimated intercept. And then I also know that the slope coefficient on the flipper length is around 50.1. And this should not be response and predictor anymore. This should be body mass, and it should be flipper length. And so what we've learned now is if we want to estimate penguin body mass, as long as we know the flipper length, we can plug the flipper length into this model, multiply it by about 50.1, subtract 5,868.5 from whatever that result is, and this will give me an estimated body mass for that corresponding penguin. All right, so that's it. We've constructed a simple linear regression model. We did that by first building a model specification, then a recipe, then a workflow. We took that workflow, we fitted it to the training data, and then we took a look at what the resulting model was, filling in those learned coefficients. Let's do the same with a multiple linear regression model. Again, there is some more work that we should be doing here. We should be interpreting the coefficients in that model. We can also, again, use that model to make predictions. Those predictions can take the form of just raw fitted values, just a single point prediction for the body mass of a penguin. They could take the form of a confidence interval, estimating the average body weight for penguins at a typical threshold of flipper length, or build a prediction interval that will capture body masses of individual penguins with a given flipper length. But again, we'll save those for another video as well if you want me to record one. The second half will go much faster. We won't go as slowly through the modeling framework. We'll just apply it again. Multiple linear regression. So we're able to extend simple linear regression to multiple linear regression by adding more predictors. We're going to assume here that each of these predictors is numerical still. If you start adding categorical variables to your model, a couple of things happen. One, you need to transform those categorical variables into something that is usable for the model. There will be a feature engineering step we need to use in order to make that happen. And two, the interpretations are not the same anymore. Those beta coefficients are not slopes if you're using categorical predictors or categorical explanatory variables. So what we're going to do here is we're going to build a multiple linear regression model. We're still going to predict penguin body mass, but now we're going to use multiple explanatory variables. So we'll use bill length, we'll use bill depth, and we'll also use flipper length to explain penguin body mass. So the model that we construct is going to look like this one. So I'll still have an intercept beta 0. I'll have a slope attached to flipper length. Again, that stays a slope because flipper length is numerical. I'll have a slope attached to bill length. Again, for the same reason, since bill length is numerical, that beta 2 is a slope. And I'll also have a slope attached to bill depth. Let's build that multiple linear regression model. And we'll do it quickly this time. So we're going to start with a model specification. So I'm just going to comment for us. Model specification here, I'm going to use MLR for multiple linear regression and spec for specification. So I have a linear regression model, and I'm going to set the engine to LM. Next, I'm going to declare my recipe. So now MLR for multiple linear regression and res for recipe. I've got the recipe, and then inside of here, I'm going to put the formula. We're still predicting penguin body mass in grams. I'm going to take a look at the columns available to me in that data set. There's body mass G. Now I'm going to predict that as explained by, so using that tilde again, and then all of the predictor variables that I want to use are going to go to the right of this tilde, separated by plus signs. So bill length plus bill depth plus flipper length and then the data set where R can find these columns is train, and we'll build that. After we have the specification and the recipe, we're going to package those together into a workflow. So MLR-WF for workflow. I'm going to use the workflow function. I'm going to pipe that to add model. MLR spec is my model, and I'm going to pipe that to add recipe. MLR res is the recipe. So now we have a workflow built that packages together the response that I'm trying to predict, the sort of ingredients that I can use in order to build up that response, and then how I'm going to prepare that response. I'm going to use a linear regression model to do it. Finally, what we're going to do is fit that model, and we're going to fit it to the training data. Again, we always fit our models to training data. So we're going to take the workflow object that we just created. We're going to pipe it to the fit function, and inside fit is going to go train. We're going to run that, and we will have our fitted model object here, MLR fit. Just like with the simple linear regression model, we're going to save model assessments and predictions to another video if you want to have one. And let's take a look at the fitted model below. So we're going to take that fitted model object, MLR fit. We're going to pipe it to extract fit engine. And we're going to pipe that to tidy, which will organize things for us and give us a little bit more insight into the model performance metrics. And then now we've got that same information. We've just got more rows in our output because we have more explanatory variables that we're using. And so we can fill in the estimated model. So I've got an intercept beta 0. That new intercept is now 6680.7. I've got a beta 1. That beta 1 is 6.66. Oops, sorry, that is not 6.66. So that coefficient I'm just going to show you is attached to flipper length here in the text that I'm writing. So I want to make sure that I grab the flipper length coefficient. Flipper length coefficient is 50.5. Sorry for that. The next slope coefficient was attached to bill length. So beta 2 is attached to bill length. I'm going to grab the bill length coefficient. That's the 6.66. And then the third beta coefficient is the one that's attached to bill depth. And in my model output, that was about 25.7 or 25.69. So let's do that, 25.69. And so at this point, if we have a penguin and we know its flipper length, its bill length, and its bill depth, we can plug those three pieces of information into this model and get an expected body mass for that penguin. All right, so again, saving all of the other stuff for a different video, but for now, I hope you found this helpful in terms of just getting comfortable with the Tidymodels modeling framework, and I hope you practice and let me know how you're doing. Thanks, everyone.